For centuries, the universe was imagined as a perfect clock. Its gears invisible, yet precise, its ticking eternal, its rhythm unbroken. Sir Isaac Newton had given the world this vision in the 17th century, a cosmos governed by universal laws, built on foundations of space and time that were absolute. Space, to Newton, was the stage upon which matter moved. Time was the metronome, ticking evenly everywhere for everyone, without variance or exception. It was an elegant vision, one that seemed to align with experience. The pendulum swings in rhythm. The planets trace their ellipses in regular arcs. A second on Earth was presumed to be the same as a second on Mars, or in the furthest corners of the heavens. The universe was mechanical, predictable, a vast celestial clock wound by divine hands. For nearly 200 years, Newton's absolutes reigned unchallenged. But in the 19th century, strange cracks began to form. Experiments with light revealed a troubling puzzle. James Clerk Maxwell's equations, written in the 1860s, showed that light should always travel at a fixed speed. Yet, if Newton was correct, that speed ought to shift depending on the motion of the observer, just as the sound of thunder changes pitch depending on whether one moves toward or away from the storm. The most famous test came in 1887. Albert Michelson and Edward Morley built an intricate instrument to measure the difference in light speed as the Earth moved through space. The result was a silence, no difference at all. Light, it seemed, was utterly indifferent to motion. Newton's framework, once unshakable, began to tremble. It was in this uncertainty that a young patent clerk in Bern, Switzerland, quietly began to question the foundations of reality. His name was Albert Einstein. In 1905, he proposed something radical. The speed of light is constant for all observers, regardless of their motion. And if this was true, then it was not light that must bend, but time itself. The consequences were staggering. Time, once absolute, became elastic. A moving clock would tick more slowly than a stationary one. Distances would contract. Simultaneity, the idea that two events could be at the same time everywhere in the universe, dissolved. What was now in one frame of reference might not be now in another. The arrow of time, once thought to be rigid and universal, fractured into countless perspectives. This was special relativity. Its equations did not merely describe the behavior of light, they redefined the nature of reality. The twin paradox was born. One twin traveling close to the speed of light would return younger than the one who remained behind. A science fiction fantasy suddenly became a prediction of mathematics. At first, the theory seemed impossible to test. Human technology could not reach such speeds. Yet nature provided its own laboratories. High-energy particles raining from space, called muons, decayed more slowly when moving at near-light velocities, just as relativity predicted. And decades later, atomic clocks flown on airplanes and later aboard satellites revealed measurable shifts in time itself. Einstein's equations were not philosophy. They were fact. But Einstein's vision did not stop there. 10 years after special relativity, in 1915, he completed a deeper revolution. Where Newton had seen space as a stage and gravity as an invisible force acting across it, Einstein unveiled a cosmos where space and time themselves were the actors. Gravity was not a force, but the bending of space-time. This was general relativity. Massive objects did not merely sit in space, they shaped it, curving its geometry, altering the flow of time. A clock on Earth's surface, deep within the planet's gravitational well, ticked more slowly than a clock orbiting far above. Time itself could be stretched and compressed by mass, just as space could. Einstein's equations described more than gentle curves. They admitted astonishing possibilities. Black holes where time seemed to grind to a halt at the event horizon, wormholes that could, in theory, connect distant points in space-time, and solutions strange, exotic, where time did not flow in a line at all, but curled into closed loops. To many, it was almost unbearable. The very notion that time was not divine, not absolute, but woven into the fabric of reality, and that this fabric could twist, bend, and perhaps fold back upon itself, was an earthquake in human thought. Einstein himself hesitated at the implications. Though his equations allowed for universes where time could loop, he resisted the idea that they reflected physical reality. Yet the seeds had been planted. Mathematicians and physicists who followed saw in his work the outlines of time machines, the possibility of stepping outside the river's current and returning upstream. General relativity was soon tested. In 1919, during a total solar eclipse, astronomers measured the bending of starlight around the sun's space itself had curved, just as Einstein predicted. Later, atomic clocks confirmed gravitational time dilation. Satellites orbiting Earth would tick differently from those on the surface, a fact now corrected constantly by the GPS systems that guide aircraft and phones. The deeper the tests went, the more the universe confirmed Einstein's unsettling truth: time is not absolute. It stretches with speed. It bends with gravity. It shatters into perspectives, each relative to the observer. This realization was more than a scientific milestone. It was a philosophical reckoning. If time is not universal, then what of history? What of cause and effect? The great metaphysical assumption that the past lies fixed, the present shared, the future waiting was no longer certain. Relativity unveiled a cosmos where time was geometry, no different from space except in the way it flowed. A four-dimensional tapestry where past and future were not yet separate domains, but regions of a larger whole. This block universe interpretation suggested that all of time, every moment that has been and will be, might already exist, carved into the structure of space-time. To live inside such a universe is to live inside a paradox of perception. We feel time flowing like a river carrying us forward. But relativity suggests the river may not flow at all. It may already exist, frozen in its entirety, while consciousness drifts through it, moment by moment, as if turning the pages of a book already written. This was Einstein's earthquake, a dismantling of the Newtonian clockwork, a shattering of absolutes, a revelation that time was not a divine constant, but a malleable fabric. The implications were immense. If time can bend, then perhaps it can break. If time is geometry, then perhaps it can be traversed, twisted, or inverted. The myths of gods stepping outside of time, the legends of mortals awakening to find centuries past, these no longer belonged only to the realm of dream. They now stood at the edge of physics, waiting for further discovery. And as the 20th century advanced, others would press deeper into Einstein's equations, exploring solutions even he was reluctant to confront. They would uncover paths where time curved back on itself, where journeys into the past were not merely fiction, but a possibility written into the mathematics of the universe. The river of time was no longer a one-way stream. It was a fabric, stretched, curved, and perhaps torn. The door to scientific time travel had been cracked open, and waiting just beyond was a discovery that would shake even Einstein himself.
Long before the language of physics was carved into mathematics, long before equations whispered of relativity and quantum fields, humanity was already haunted by a question. Is time unbreakable? In every civilization, across continents and centuries, the flow of time was felt as both an endless gift and a merciless prison. It bore the young into age, kingdoms into ruin, and stars into silence. Yet the imagination of humankind has always resisted confinement. Where the river of time seemed absolute, myths began to suggest escape. In the stories of ancient Greece, time was personified as Kronos, a primordial being who devoured his own children, an image of time's hunger. Yet alongside him stood the gods of Olympus, immortal figures who seemed to walk freely outside the mortal current, untouched by decay. Heroes occasionally stumbled into strange domains where time moved differently. In the myth of Endymion, the shepherd who slept eternally, his youth preserved by divine will, one hears the first echo of suspended time, a pause in the relentless march of mortality. In India, the idea of Kalachakra, the wheel of time, envisioned existence not as a straight arrow but as a cycle, ages repeating endlessly, destinies returning in vast cosmic rhythms. Time was not a one-way stream but a circle, turning upon itself, allowing rebirth and recurrence. Ancient texts such as the Mahabharata speak of journeys where time dilates in strange ways. a warrior ascends to the realm of the gods, and upon his return, discovers that centuries have passed on Earth. A poetic tale, yet one that strangely foreshadows the scientific revelation of time dilation millennia later. In China, philosophers of the Tao pondered the relativity of perception, that the passage of hours or lifetimes might depend on the vantage point of the observer. In the legend of the Yellow Emperor, Huangdi journeys to the heavens for what feels like a short communion with celestial beings, only to return and find that generations have passed on Earth. Myth, once again, brushed against a truth modern physics would eventually describe with precision. That time is not universal, but depends upon where and how one moves. These ancient visions, Greek, Indian, Chinese, and countless others, planted the first seeds. They were not yet theories, nor hypotheses tested against nature. They were intuitive stirrings, reflections of humanity's refusal to believe in finality. Time, in these early mirrors, could be cyclical, malleable, even escapable. As centuries passed, stories of time's bending found their way into early literature. In Japan's tale of Urashima Taro, a fisherman visits the undersea palace of the dragon god, believing only days have passed, only to return to the surface and discover centuries gone. In the European folktale of the Seven Sleepers of Ephesus, young men awaken from a miraculous slumber to find their world transformed, time having leapt forward without them. In the Persian tale of the Copper City, travelers find themselves in places where time flows differently, accelerated or slowed, alien to the world they left behind. These are not scientific accounts, yet they reveal something extraordinary. Across cultures with no shared contact, humanity envisioned the same phenomenon, the relativity of time. Each culture painted it with its own symbols, gods, palaces, dreams, but the idea was the same. That time could break, that time could skip, that the human experience of its flow might not be universal. Later, as philosophy matured, questions grew sharper. The ancient Greeks debated whether time existed independently of change, or whether it was simply the measure of movement. Plato described time as the moving image of eternity. Aristotle defined it as the measure of change according to before and after. Each definition circled a profound insight, that time is inseparable from perception, and perhaps from the very structure of reality. In India, Buddhist philosophers spoke of ksana, the smallest indivisible moment of time, suggesting that reality itself might be composed of discrete instants rather than continuous flow. In China, the historian Sima Qian described time as a repeating cycle of dynasties rising and falling, history itself conceived as temporal recurrence. These were not yet scientific theories, but they carried seeds that physics would later cultivate. The possibility that time could be granular, curved, or cyclical. By the Middle Ages, stories of temporal distortion became allegories for morality and spirituality. Christian mystics envisioned time as a linear arrow, beginning with creation, ending with judgment. Yet in their visions of eternal paradise, time dissolved entirely, offering an existence beyond its reach. The notion that time could be conquered was now entwined with salvation itself. The Renaissance and Enlightenment would shift the lens again. Writers began to imagine not only divine or mystical interruptions of time, but human journeys through it. In the 18th and 19th centuries, literature introduced what myths had only hinted at: deliberate voyages through time. Washington Irving's Rip Van Winkle fell asleep for 20 years, awakening in a new America. H.G. Wells' The Time Machine offered, for the first time, a mechanical vehicle that carried its rider across centuries at will. It is here, in Wells' vision, that the myth began to crystallize into something new. No longer only the realm of gods or dreams, time travel became a question of technology, of mechanism, of science. And with that transformation, a new era dawned. For thousands of years, humanity had only dreamed. Time was imagined as a cycle, a circle, a divine force, a veil pierced by heroes and gods. But in the coming century, equations would begin to speak. And when they did, they would suggest something extraordinary: that these ancient dreams were not entirely wrong. The river of time, once thought to be eternal and unyielding, would soon reveal cracks in its banks. Myths would meet mathematics, and the story of time travel would shift from whispered legend to scientific possibility.
Time, an invisible river, flowing endlessly, silently, without pause. It carries galaxies upon its currents, lifts the lives of stars, and sweeps the fragile breath of humankind along its surface. Every heartbeat, every rise of dawn, is carried forward by its tide. Yet the river has always appeared mercilessly one way, bearing all things into the unknown ocean of the future. But beneath the stillness of its waters, questions have always stirred. What if the current could be reversed? What if the river was not a prison, but a maze of hidden channels, waiting to be discovered? Humanity has whispered of this possibility for millennia. In myths and in dreams, in equations and experiments, there lingers the hope that time is not a wall, but a doorway. Time travel, at once a promise and a terror. The promise of rewriting what was lost, of mending mistakes, of peering beyond tomorrow's veil. Yet also the terror of paradox, where cause collapses into effect and history devours itself. A universe that permits such journeys may unravel its own logic, tearing apart the fragile web of reality. And yet, in the language of physics, the impossible begins to glimmer. In Einstein's equations, in the curves of space-time, in the strange geometry of wormholes and cosmic strings, there emerge cracks in the riverbank. Doorways hinted at by mathematics, shadows of paths not yet taken. This is the story of time travel, not as fantasy, but as science. A story where myth collides with relativity, where imagination meets the hard boundaries of the cosmos. A journey into humanity's oldest dream, and perhaps its deepest fear.
The 20th century was still trembling from Einstein's revelations when a new and unsettling question arose. If space-time could bend and twist, if clocks could slow and paths could curve, then perhaps the greatest dream of myth and story was no longer impossible. Perhaps time itself could loop. Until then, time travel had belonged to the realm of imagination, to myths of sleeping kings, to H.G. Wells' gleaming brass machine. But in 1949, mathematics gave birth to something more disquieting, a vision not from poetry, but from the hard geometry of Einstein's equations. The mathematician was Kurt Gödel, already famous for proving the incompleteness of logic itself. He was a close friend of Einstein's at Princeton, where the two would often walk the tree-lined paths of the Institute for Advanced Study, discussing the foundations of reality. Where Einstein had dismantled the absoluteness of time, Gödel took the next, more dangerous step, exploring whether time could be undone. Gödel studied Einstein's field equations of general relativity and searched for unusual solutions. To his astonishment, he discovered one that described a universe in perpetual rotation, a vast cosmic whirlpool where the fabric of space-time itself turned endlessly. In such a universe, the flow of time was not linear. Paths through space-time could be traced in great arcs that bent back upon themselves. These were called closed time-like curves, trajectories where a traveler, moving always forward in their own proper time, could eventually return to their own past. The implications were staggering. Einstein's theory, meant to describe the geometry of stars and gravity, contained within it the possibility of a time machine. No gears, no levers, no fiction, only the geometry of the cosmos, reshaping causality. Physicists and philosophers alike struggled to absorb what this meant. If the equations permitted travel into the past, what then of paradoxes? Could an event cause itself? Could an effect erase its own cause? Would history collapse under contradictions, or would it fold into self-consistent loops? The neat arrow of time, once thought to be unbreakable, was suddenly uncertain. Einstein himself was unsettled. Though he admired Gödel, he resisted the implications of his rotating universe. To Einstein, the physical cosmos seemed stable, expanding, not eternally spinning. He doubted such a solution corresponded to reality. And yet, the mathematics was undeniable. General relativity admitted worlds where time could be navigated in circles, worlds where the past was no longer sealed. It was here that the concept of time machines entered scientific thought in earnest. No longer confined to stories, the possibility of temporal travel was encoded in the most successful theory of gravity humanity had ever known. Gödel had not built a time machine, but he had proven, in principle, that physics did not forbid one. The astonishment of the scientific community was layered with unease. If closed time-like curves were real, then causality, the bedrock of science itself, was at risk. Every experiment relies on cause preceding effect, on tomorrow not reshaping yesterday. But Gödel's solution suggested that under the right cosmic conditions, this foundation could crumble. The paradoxes were not trivial. Imagine a traveler returning to the past and preventing their own journey. Imagine knowledge without origin, a book handed from the future to the past, written by no author, existing in a loop forever. Logic, like time, seemed to twist upon itself. And yet, not all found this horrifying. Some saw beauty in the possibility of self-consistency, the idea that events might conspire to avoid paradox, that time itself might weave its own corrections. In such a universe, free will might dissolve, but history would remain unbroken. Every loop would be seamless, every action folded into inevitability. The discovery of closed time-like curves marked a turning point. The question was no longer whether time travel could be imagined, but whether the universe itself permitted or forbade it. For the first time, serious physicists confronted a possibility that echoed the oldest human dreams, that the river of time could bend back toward its source. In the decades that followed, Gödel's unsettling universe became a reference point, a reminder that Einstein's equations contained far more than the human mind expected. New solutions were explored, wormholes that could act as shortcuts across space-time, cosmic strings that could twist time into loops. Each was more speculative than the last, but all shared the same unsettling heritage, the realization that general relativity did not close the door on time travel. It left it ajar. For Einstein, the unease never faded. He once confessed that Gödel's work was of profound interest, but he resisted the notion that such universes described reality. To him, the cosmos was vast but stable, governed by order, not by temporal spirals. Yet, even in his doubt, the seed was planted. What Gödel had shown was not that time travel existed, but that physics could not easily deny it. The dream of stepping outside the current of time, once confined to myth, had entered the halls of science. From this moment onward, the mystery of time was no longer only philosophical. It became experimental. Could such loops be found in nature? Could they be created in laboratories? Or would deeper laws, still hidden, still undiscovered, rise to forbid them? Gödel's rotating universe was a mathematical artifact, perhaps not reflective of reality as we see it. But it opened a doorway Einstein himself chose not to walk through, a doorway into questions that would dominate the century to come. The birth of scientific time travel was not the construction of a machine, but the collapse of certainty. Causality, once unshakable, now trembled. And with that tremor, the story of time travel began to leave myth behind and step into physics, a story that would only deepen as experiments reached for the very edge of time itself.
In the imagination of physics, one thought experiment became a symbol of relativity's unsettling power. Two siblings, born at the same moment, identical in every way. One remains on Earth. The other climbs into a starship and sails near the speed of light. When the traveler returns, they step out younger than their twin, as though time itself had played favorites. This was the twin paradox, first posed in the early years of relativity. To many, it seemed absurd. How could the same laws of physics allow two people, once united, to experience time so differently? For centuries, time had been regarded as a universal current, flowing equally for all. But Einstein's equations revealed otherwise. The flow of time was not absolute. It was elastic, stretching, and compressing depending on motion and gravity. The twin who traveled near light speed would live through fewer moments. Their heartbeats would slow, their clocks would tick more reluctantly. Their very experience of existence would unfold at a different pace. And when they returned, Earth's clocks would have recorded more time than their own. The paradox was only apparent. Motion and acceleration had distinguished their paths, leaving the traveler younger, the stay-at-home older. For decades, this thought experiment remained an elegant but untested story. Yet nature does not bow to disbelief. In time, the paradox left the realm of imagination and entered the laboratory. By the mid-20th century, physicists began to test Einstein's predictions with exquisite precision. The tool was the atomic clock, a device that counted the oscillations of atoms with unerring regularity. In 1971, the Haffel-Keating experiment flew atomic clocks aboard commercial airliners, circling the Earth eastward and westward. When the planes landed, the results were undeniable. The airborne clocks had diverged from those left on the ground, lagging or leaping ahead by tiny but measurable amounts, exactly as relativity foretold. Time had shifted not in thought experiments but in steel, sky, and cesium atoms. Further confirmations followed. Satellites carrying atomic clocks revealed the dual influence of relativity. Orbiting high above Earth, they tick faster than clocks on the ground because gravity is weaker, yet slower because of their motion. These competing effects balance delicately, but neither can be ignored. Indeed, every smartphone today, every car navigation system, every ship at sea owes its accuracy to this truth. The Global Positioning System, a constellation of satellites circling Earth, functions only because engineers correct for relativistic time dilation. Without Einstein's equations, GPS would drift kilometers off course each day. The theory of relativity, once dismissed as abstract, now silently guides airplanes, maps cities, and synchronizes economies. Humanity lives inside the proof of time's flexibility. In these experiments, the twin paradox ceased to be paradox at all. Time travel into the future, once the domain of speculative fiction, became established fact. The effect may be measured in billionths of a second, yet the principle remains. Every astronaut aboard the International Space Station, moving at 28,000 kilometers per hour, ages slightly less than those who remain on Earth. A few microseconds lost with each mission, imperceptible to the body, but carved into the ledger of physics. The implications stretch far beyond the laboratory. If technology could propel a vessel to near-light speed, the twin paradox would no longer be a story, but an experience. A journey of decades could carry a traveler into Earth's distant future, while their own body aged only a few years. What began as a mathematical quirk had blossomed into the realization that one-way journeys into tomorrow are not only possible, but inevitable under the laws of relativity. This form of time travel is unidirectional and unyielding. There is no symmetry, no return ticket. The traveler cannot leap back into their own past. They can only arrive in a future that unfolds without them. Yet in this inevitability lies both wonder and sorrow. Time dilation does not violate the arrow of time. It stretches it like a taut thread pulled thinner and longer in one direction. The twin paradox reveals a cosmos where each observer carries their own clock. Each heartbeat is its own rhythm, and time itself is no universal melody, but a polyphony of shifting tempos. On the scale of human life, the differences are small. On the scale of stars and speeds close to light, the differences become a new kind of destiny. What was once paradox has become proof. The universe does not bind all beings to the same pace. It allows escape, if only forward, if only into futures unseen. The twin paradox is no longer confined to thought. It is written into the circuitry of satellites, into the motions of astronauts, into the very devices that guide human life on Earth each day. And so, the first experiments in relativistic time were not steps into myth, but steps into reality. The traveler who returns younger is no longer a dream. It is physics, precise, measurable, inevitable. Humanity has not yet built a starship to chase the speed of light, but already, with every orbit and every signal sent from sky to ground, the proof resounds. Time is not absolute. It is a river that bends, quickens, and slows, carrying each voyager on their own unique course. In the imagination of physics, one thought experiment became a symbol of relativity's unsettling power. Two siblings, born at the same moment, identical in every way. One remains on Earth. The other climbs into a starship and sails near the speed of light. When the traveler returns, they step out younger than their twin, as though time itself had played favorites. This was the twin paradox, first posed in the early years of relativity. To many, it seemed absurd. How could the same laws of physics allow two people, once united, to experience time so differently? For centuries, time had been regarded as a universal current, flowing equally for all. But Einstein's equations revealed otherwise. The flow of time was not absolute. It was elastic, stretching and compressing depending on motion and gravity. The twin who traveled near light speed would live through fewer moments. Their heartbeats would slow, their clocks would tick more reluctantly. Their very experience of existence would unfold at a different pace. And when they returned, Earth's clocks would have recorded more time than their own. The paradox was only apparent. Motion and acceleration had distinguished their paths, leaving the traveler younger, the stay-at-home older. For decades, this thought experiment remained an elegant but untested story. Yet nature does not bow to disbelief. In time, the paradox left the realm of imagination and entered the laboratory. By the mid-20th century, physicists began to test Einstein's predictions with exquisite precision. The tool was the atomic clock, a device that counted the oscillations of atoms with unerring regularity. In 1971, the Haffel-Keating experiment flew atomic clocks aboard commercial airliners, circling the Earth eastward and westward. When the planes landed, the results were undeniable. The airborne clocks had diverged from those left on the ground, lagging or leaping ahead by tiny but measurable amounts, exactly as relativity foretold. Time had shifted not in thought experiments but in steel, sky, and cesium atoms. Further confirmations followed. Satellites carrying atomic clocks revealed the dual influence of relativity. Orbiting high above Earth, they tick faster than clocks on the ground because gravity is weaker, yet slower because of their motion. These competing effects balance delicately, but neither can be ignored. Indeed, every smartphone today, every car navigation system, every ship at sea owes its accuracy to this truth. The Global Positioning System, a constellation of satellites circling Earth, functions only because engineers correct for relativistic time dilation. Without Einstein's equations, GPS would drift kilometers off course each day. The theory of relativity, once dismissed as abstract, now silently guides airplanes, maps cities, and synchronizes economies. Humanity lives inside the proof of time's flexibility. In these experiments, the twin paradox ceased to be paradox at all. Time travel into the future, once the domain of speculative fiction, became established fact. The effect may be measured in billionths of a second, yet the principle remains. Every astronaut aboard the International Space Station, moving at 28,000 kilometers per hour, ages slightly less than those who remain on Earth. A few microseconds lost with each mission, imperceptible to the body, but carved into the ledger of physics. The implications stretch far beyond the laboratory. If technology could propel a vessel to near-light speed, the twin paradox would no longer be a story, but an experience. A journey of decades could carry a traveler into Earth's distant future, while their own body aged only a few years. What began as a mathematical quirk had blossomed into the realization that one-way journeys into tomorrow are not only possible, but inevitable under the laws of relativity. This form of time travel is unidirectional and unyielding. There is no symmetry, no return ticket. The traveler cannot leap back into their own past. They can only arrive in a future that unfolds without them. Yet in this inevitability lies both wonder and sorrow. Time dilation does not violate the arrow of time. It stretches it like a taut thread pulled thinner and longer in one direction. The twin paradox reveals a cosmos where each observer carries their own clock. Each heartbeat is its own rhythm, and time itself is no universal melody, but a polyphony of shifting tempos. On the scale of human life, the differences are small. On the scale of stars and speeds close to light, the differences become a new kind of destiny. What was once paradox has become proof. The universe does not bind all beings to the same pace. It allows escape, if only forward, if only into futures unseen. The twin paradox is no longer confined to thought. It is written into the circuitry of satellites, into the motions of astronauts, into the very devices that guide human life on Earth each day. And so, the first experiments in relativistic time were not steps into myth, but steps into reality. The traveler who returns younger is no longer a dream. It is physics, precise, measurable, inevitable. Humanity has not yet built a starship to chase the speed of light, But already, with every orbit and every signal sent from sky to ground, the proof resounds. Time is not absolute. It is a river that bends, quickens, and slows, carrying each voyager on their own unique course. In the deep mathematics of Einstein's equations, there lurk strange corridors, hidden within the folds of spacetime. They are not stars, nor planets, nor galaxies. They are passages, shortcuts through the very fabric of reality itself. Physicists came to call them wormholes. The idea first appeared in 1935, when Albert Einstein and Nathan Rosen searched for a way to connect two regions of spacetime. Their solution resembled a bridge, a throat linking distant points in the cosmos. Today, these are called Einstein-Rosen bridges. To the human imagination, they became tunnels through the universe, cosmic subways that might allow one to step across impossible distances in a heartbeat. But in their original form, these bridges were fragile. They collapsed too quickly for anything to pass through. Like soap bubbles bursting at the instant of their creation, they seemed destined to remain mathematical ghosts, not physical doorways. Yet the question lingered. Could nature allow wormholes to remain open? Could they become stable, traversable, even usable as gateways not only across space but across time? In the 1980s, physicist Kip Thorne and his colleagues took the question seriously. Inspired in part by a challenge from science fiction, they asked whether Einstein's equations permitted a wormhole large enough and stable enough for a human traveler. The mathematics gave a surprising answer: yes, but only if the wormhole were threaded with something profoundly exotic. This substance would not be ordinary matter, nor even the familiar energy of stars. It would require negative energy density, a form of matter that pushes instead of pulls, that bends spacetime outward instead of inward. Physicists call it exotic matter. In tiny glimpses, nature hints that such strangeness exists. Quantum field theory predicts phenomena where energy can take negative values for brief moments, as in the Casimir effect, where empty space between two metal plates is altered by quantum fluctuations. If such effects could be harnessed and magnified, they might serve as the scaffolding to hold a wormhole open. Without it, the throat would collapse, crushing traveler and dream alike. The possibility electrified scientific thought. For if a wormhole could be stabilized, relativity offered no barrier to turning it into a time machine. By accelerating one mouth of the wormhole near the speed of light, or placing it near a strong gravitational field, time dilation would cause one end to age differently than the other. Step through, and one would not only cross space, but emerge in another epoch. The mathematics whispered of closed loops in time, of journeys to the past as well as the future. Yet, with these whispers came paradox. Could such paths unravel causality, allowing effect to precede cause, rewriting history itself? Physicists debated fiercely. Some argued that the laws of quantum mechanics would conspire to prevent paradoxes, that reality would censor impossible timelines. Others saw no such protection written into the equations. If wormholes embody the fantasy of tunnels through spacetime, then cosmic strings represent a darker vision. Relics of creation itself, stretched across the universe like scars. Cosmic strings are hypothetical, thin, ultradense filaments of energy predicted by certain theories of the early universe. If they exist, they would be thinner than an atom, yet more massive per length than entire mountains. They would warp spacetime with their passage, leaving behind gravitational imprints strong enough to lens light from distant galaxies. Physicists have speculated that two such strings, passing by one another at near-light speeds, could twist spacetime into closed time-like curves, loops in which time circles back on itself. A traveler tracing such a loop could, in principle, return to their own past. Yet the evidence for cosmic strings remains elusive. Astronomers have searched the sky for their telltale signatures. Sudden gravitational lensing events, sharp discontinuities in the cosmic microwave background. To date, no definitive trace has been found, but absence is not proof of non-existence. If strings are real, they may be rare, hiding in the vastness of the cosmos, remnants of primordial energies locked away since the first moments after the Big Bang. Both wormholes and cosmic strings embody the same haunting truth. The equations of relativity permit paths that defy ordinary time. They suggest a universe more malleable, more strange, than intuition allows. Yet each also confronts humanity with barriers. Exotic matter that has never been harnessed, cosmic relics that may never be found. Still, the allure remains. Wormholes offer the dream of stepping through a doorway and finding oneself centuries away. Cosmic strings hint at the possibility that time itself may be knotted, twisted, or looped. Neither vision has been proven real, but in their shadows, one glimpses the unsettling possibility that the cosmos may contain hidden architectures of time, waiting in silence for discovery. For now, they remain dark paths, theoretical, mysterious, dangerous. They remind us that space-time is not a stage upon which events unfold, but an active, dynamic entity, capable of folding in upon itself, bending not only distance but destiny.
Time travel, if it is possible, does not simply bend the imagination. It fractures the very logic upon which reality seems to rest. For in the mirror of the past, questions arise that do not yield to mathematics alone. They summon dilemmas where cause and effect collapse into one another, where the thread of history tangles itself into knots. The most famous of these riddles is known as the grandfather paradox. Imagine a traveler who journeys backward, arriving decades before their birth. If that traveler were to prevent the existence of their own ancestor, their grandfather, they would, by consequence, erase themselves from history. And yet, if they were erased, who then made the journey? Cause unravels from effect. Effect vanishes from cause. The paradox swallows itself whole. This is not merely a thought game. It exposes the most profound vulnerability of time travel, the violation of causality. The universe appears to operate on chains of reason, where events unfold from what came before. Time travel to the past threatens to sever this chain, leaving logic adrift. But there are stranger paradoxes still. Consider the notion of a causal loop, an object or a piece of information that has no origin. A book handed to a traveler in the future, carried back in time, and published long before it was ever written. Who authored it? The loop contains no beginning, no first spark of creation. The information exists only because it is trapped within the cycle. To the equations of relativity, such loops are not forbidden. They are possible solutions where consistency replaces origin. But to human reason, they carry an unsettling truth that some things may exist without a cause. In the 1980s, physicist Igor Novikov proposed a way to resolve these dilemmas. Known as the Novikov self-consistency principle, it suggests that the universe is immune to paradox. A traveler may journey to the past, but their actions will only ever fulfill history, not alter it. They may attempt to prevent their grandfather's survival, yet circumstances will intervene to ensure failure. The laws of physics, Novikov argued, conspire to protect causality. Events may bend, but they cannot be broken. This principle offers a universe where time travel is self-correcting, where the past is a tapestry already woven, resistant to unraveling. It transforms the traveler from a disruptor into a participant in destiny's script, bound by the inevitability of what has already been written. And yet, not all agree with this deterministic vision. Quantum theory, with its branching probabilities, suggests another possibility, the multiverse interpretation. In this framework, paradox dissolves not by prevention, but by proliferation. Each action splits reality into new branches. A traveler who prevents their grandfather's survival does not erase themselves. They simply move into a different timeline, one where their origin diverges. The paradox is not resolved within a single universe, but spread across an infinite sea of them. This idea transforms time travel from a forbidden act into a cosmic migration. Each journey creates a fork, each decision a new reality. The grandfather paradox no longer threatens existence, for in one world the traveler is erased, and in another, they endure. But this solution comes at a cost. It multiplies worlds endlessly, raising the question of whether all histories exist somewhere, playing out in infinite variations. Science stands divided. Relativity permits closed time-like curves, pathways that could loop through the past. Novikov's principle suggests consistency will shield reality from contradiction. Quantum theory whispers of branching worlds, of infinite versions of events. None has been proven. All remain possible. But behind these paradoxes lies a deeper, more haunting reflection. Time is not merely a dimension to be measured. It is the scaffolding of reality's logic. To bend it backward is to place causality itself at risk. If the past can be rewritten, then history is no longer secure. If loops can exist without origin, then creation itself loses meaning. And if multiverses are real, then every moment, every choice fractures into countless paths, leaving behind shadows of realities where different histories unfold. In such a cosmos, the traveler does not conquer paradox. They become lost in an infinity of truths. For now, paradoxes remain unsolved riddles, perched on the edge of mathematics and philosophy. They are the warning signs that appear when human thought dares to step across the threshold of time. Like cracks in the glass of reality, they remind us that some mysteries may resist resolution, standing as eternal guardians of the past. Time travel may be possible in theory, but paradox shows us the price, the stability of causality, the certainty of history, and perhaps even the meaning of existence itself. Time is not simply a river flowing forward. When bent backward, it becomes a mirror that fractures. Logic begins to tremble. Cause and effect, the twin pillars of reality, stumble into contradictions. The mathematics of relativity may allow closed loops through space-time, but philosophy warns of something stranger: paradox. The most enduring of these riddles is the grandfather paradox, a thought experiment so disarmingly simple that it unsettles even the most rigorous minds. A traveler journeys into the past, decades before their own birth. In an act of interference, deliberate or accidental, they prevent the life of their ancestor, their grandfather. If the ancestor falls, then the traveler's parent is never born. The traveler themselves can never exist. And yet, without existing, who is it that struck the blow? Cause destroys effect. Effect destroys cause. The paradox folds back on itself like an impossible knot, an Ouroboros consuming its own tail. This dilemma is more than speculation. It is a test of whether time itself obeys the logic on which reality seems to rest. Physics can describe loops in space-time, but if those loops unravel causality, then the universe threatens to collapse into incoherence. The grandfather paradox stands as a warning sign at the frontier, a place where the laws of the cosmos risk contradiction. But paradox wears many faces. Consider the eerie riddle of the causal loop. Here, no contradictions appear. Instead, the mystery lies in the absence of origin. Imagine a book. A time traveler carries it into the past and hands it to a young writer. That writer publishes it, and decades later, the same book is given to the traveler, who once more carries it backward. The loop is complete. But who then wrote the book? The knowledge exists, but without a beginning. Its presence is eternal, suspended in a cycle without a first cause. Einstein's equations do not forbid such loops. In the labyrinth of relativity, they stand as valid, self-consistent solutions. Yet to human thought, they reveal a disquieting possibility that not everything which exists must be born. Some things may simply be closed circuits of information, objects, or actions locked in repetition across time. Seeking an answer, physicist Igor Novikov proposed a principle that still echoes through debates today. Known as the Novikov self-consistency principle, it suggests that the universe protects itself from paradox. Time travel, if it occurs, cannot rewrite the past. Every action performed by a traveler would be woven seamlessly into history, consistent with what already happened. The traveler might attempt to kill their grandfather, the gun might jam, the attempt might fail, or circumstances might intervene in ways they could not foresee. History, Novikov argued, is resistant to contradiction. The past cannot be altered, only fulfilled. This paints a picture of a universe that is not fragile, but resilient. A cosmic tapestry already woven, in which each thread, even the journeys of travelers through time, is fixed in its place. To move backward is not to change destiny, but to participate in it. The paradox dissolves, not because it is avoided, but because it was never possible in the first place. Yet another possibility arises from the strange domain of quantum theory. Where relativity describes the geometry of space-time, quantum mechanics whispers of probabilities branching at every decision. Here emerges the multiverse interpretation. In this view, paradoxes are illusions of perspective. A traveler who kills their ancestor does not erase themselves. They simply cross into a new branch of reality where the lineage diverges. In one universe, their grandfather survives and they are born. In another, the line is cut and the traveler belongs to a different strand of history altogether. This interpretation does not protect causality by preventing contradiction. It dissolves contradiction across infinity. Every action, every possibility, splits the cosmos into countless versions of itself. Paradoxes lose their sting because all outcomes exist somewhere. The traveler may vanish in one world but continue in another. Time travel does not threaten reality, it multiplies it endlessly. But such abundance raises its own unease. If the multiverse is real, then every decision, every motion, fractures existence into countless shadows. Histories diverge, lives multiply, worlds proliferate without end. For every action taken, infinite versions of the universe play out in parallel. The paradox is solved, but meaning itself begins to blur. What does it mean to act if every act is already taken in another branch? What does it mean to choose if every choice is already lived? Thus, the paradox of time is not merely a scientific puzzle. It is a mirror held against existence itself. The grandfather paradox challenges the security of history. The causal loop questions the very idea of origins. Novikov's principle restores consistency, but leaves us bound to destiny. The multiverse frees us from contradiction, but drowns us in infinity. No experiment has resolved these questions. No time traveler has returned to clarify whether the past resists change, whether loops without beginning exist, or whether multiverses truly proliferate in silence beyond our sight. For now, the paradoxes remain as thought experiments, signposts marking the boundaries of our understanding. Yet they carry weight, even in speculation. They remind science that time travel, if it is real, will not be a simple extension of movement. It will shake the foundations of logic itself. The paradoxes warn that behind the elegance of relativity, behind the probabilities of quantum mechanics, lies a deeper mystery: whether the universe can endure the bending of causality. To dream of traveling through time is to dream of stepping into these paradoxes. It is to risk encountering a universe that denies change, or one that denies origin, or one that multiplies without end. Time travel may be possible, but paradox reveals the cost. At stake is nothing less than causality, history, and the very coherence of reality itself.
At the smallest scales of existence, time begins to tremble. The smooth river of seconds and minutes fractures into a restless sea, its surface foaming with uncertainty. In the quantum world, events are not fixed, but suspended in probabilities. The future is not yet chosen, and the past is not entirely secure. It is here, within the strange mechanics of the subatomic, that the arrow of time begins to blur. Einstein's theory of relativity speaks of time as a dimension, woven seamlessly with space into a four-dimensional fabric. It describes how clocks tick more slowly in stronger gravity, how the passage of time is never universal, but relative to perspective. Yet, relativity is smooth and continuous, a geometry unbroken. Quantum mechanics, by contrast, is discrete and unpredictable. It deals not in certainties, but in possibilities. When these two visions collide, when the vast cosmic geometry of relativity meets the restless quantum sea, contradictions erupt. Nowhere is this more evident than in the riddle physicists call the problem of time. In the 1960s, John Wheeler and Bryce DeWitt sought to unify quantum mechanics with Einstein's general relativity. Their attempt gave rise to the Wheeler-DeWitt equation, a mathematical framework intended to describe the quantum state of the entire universe. But this equation contained a haunting silence. Time itself had disappeared. Unlike Schrödinger's equation, which describes how quantum states evolve with time, the Wheeler-DeWitt equation is timeless. It implies that at the most fundamental level, the universe simply is, eternal, frozen, unchanging. The flow of time, so immediate in human experience, may be an illusion born from perspective, not a fundamental feature of reality. This is the first paradox of quantum time, a universe without clocks. If the equation is correct, then what we call the passage of time is merely the unfolding of correlations, the change of one system relative to another. Time does not exist as a river, but as a tapestry, already complete, in which every moment coexists with every other. Yet, within quantum theory itself, traces of time's rebellion appear again and again. Consider the interpretation of Richard Feynman, who transformed the understanding of particles by reimagining their paths. In his diagrams, electrons and positrons, matter and antimatter, were not distinct particles, but reflections across time. A positron could be understood as an electron moving backward, retracing history in reverse. To the mathematics of quantum electrodynamics, such backward journeys through time are not forbidden. They are integral to the very structure of the laws. In this vision, the fabric of reality allows subtle exchanges between past and future. The universe is not a strict progression from cause to effect, but a dialogue between forward and backward flows, balanced across time's axis. What appears to us as antimatter might, at its core, be the signature of time itself running in reverse. The strangeness deepens with the phenomenon of quantum entanglement. When two particles are entangled, their properties become linked, no matter the distance that separates them. Measure one, and the other responds instantly, as though no space lies between them. Einstein himself called it spooky action at a distance, unsettled by the suggestion that information could leap across the void faster than light. But within certain interpretations, entanglement may not only stretch across space, it may also weave across time. In experiments probing quantum retrocausality, entangled particles appear to share information in ways that blur the distinction between past and future. Decisions made in the present seem to ripple backward, shaping the outcomes of events that occurred earlier. The arrow of time bends, not only in imagination, but in the mathematics of quantum theory. Physicists debate whether such retrocausality is real or merely an artifact of interpretation. Yet the experiments persist. In delayed choice tests, particles appear to adjust their behavior based on measurements made after they have already been detected. It is as though the present rewrites the past, and the past anticipates the future, creating a seamless dialogue that defies ordinary chronology. This is the second paradox of quantum time, that causality, the chain of reason and consequence, may not be as linear as it seems. The quantum world may allow influence to ripple both forward and backward, unconfined by the strict arrow we observe in daily life. And yet, the greatest mystery remains the reconciliation of these ideas with gravity, the force that shapes the universe on its grandest scales. Relativity and quantum mechanics remain estranged, each resistant to union. In relativity, time is geometric, continuous, and woven into space-time itself. In quantum mechanics, time is elusive, sometimes absent, sometimes reversible, sometimes tangled in ways that mock human intuition. The search for quantum gravity, a theory that unites the very large and the very small, is, at its heart, a search for time itself. Is time emergent, like temperature, arising only from the collective behavior of deeper elements? Or is it fundamental, a bedrock of the universe as real as space? The Wheeler-DeWitt equation suggests timelessness. Feynman's diagrams suggest reversibility. Entanglement suggests loops across both distance and chronology. Each whispers a different truth, yet none delivers the final answer. The implications reach beyond science into philosophy. If time is an illusion, then the present moment is not unique. The future already exists, waiting silently, as immutable as the past. If particles move backward as well as forward, then causality is not absolute, and events may influence each other across the boundaries of chronology. If retrocausality is real, then the universe is not a line, but a web, in which the strands of influence run both ways. What then becomes of human experience? To live is to feel the passage of time, the unfolding of stories, the weight of memory, the hope of possibility. If the quantum world erases time, or bends it into loops, what does it mean to remember or to choose? Perhaps memory itself is the illusion, not a record of the past, but a construction of the present, arranged to give coherence to a timeless reality. Quantum time does not provide answers. It provides riddles, cracks in the foundation of our understanding, glimpses into a reality stranger than imagination. It reminds us that time is not a settled concept, but a mystery at the heart of physics. Whether timeless, reversible, or entangled across past and future, it resists the comfort of certainty. The paradoxes of relativity showed that time is not universal. The paradoxes of quantum mechanics suggest that it may not even exist as we think it does. In the collision of these two great theories, time itself becomes unstable. And until they are reconciled, the riddle of time will remain, a silence at the core of the cosmos, waiting to be broken. In the grand theater of physics, theories are like constellations, beautiful, luminous, yet distant. To bring them closer, scientists turn to the laboratory, where ideas must face the test of reality. Here, among magnets and lasers, particle accelerators and quantum computers, humanity dares to probe the boundaries of time itself. These are not idle curiosities, but careful, fragile steps, walking the edge between imagination and proof. At the heart of Europe, beneath the border of Switzerland and France, lies the Large Hadron Collider, a vast ring of superconducting magnets stretching for 27 kilometers. It was built to smash particles together at energies never before achieved, revealing hidden structures of matter and glimpses of the earliest universe. But within its circular tunnels, scientists have also searched for stranger signatures, closed time-like curves, the mathematical pathways in space-time that, in theory, could allow a particle to circle back into its own past. General relativity permits such curves, twisted corridors through space-time where the arrow of time bends into a loop. Some solutions, like Gödel's rotating universe or the warped throats of wormholes, suggest the possibility of journeys that defy chronology. But in the LHC, no traveler is expected to step out of history. Instead, physicists look for subtle imprints, patterns in collisions that would hint at particles behaving as though they had interacted with their own past selves. So far, the data remains silent. No closed loops have emerged, no whispers of time-traveling quarks. Yet the very act of searching is profound, a declaration that humanity is willing to test even the most radical boundaries of physics. Beyond the colossal machinery of accelerators, other experiments unfold on a gentler scale within laboratories of light. In the realm of optics, researchers perform tests where photons, the quanta of light, appear to reach backward, influencing measurements already made. These are known as delayed choice experiments, modern descendants of the double-slit experiment that first revealed the wave-particle duality of quantum mechanics. In these setups, a photon passes through an apparatus, but the decision of how to measure it is delayed until after the photon has already entered. Astonishingly, the photon behaves as though it had known the future choice all along. If the experimenter chooses to measure it as a wave, the photon displays interference, even though, at the time it passed through, no such setup existed. If measured as a particle, it behaves as a single localized point, retroactively erasing the interference pattern. The implications are unsettling. Does the present decision rewrite the past event? Or does the past event never truly exist until the present choice is made? In either case, the ordinary separation between past and present seems blurred. Such experiments do not yet prove retrocausality, but they stretch causality to its thinnest edge, revealing a quantum world in which time's order is far less rigid than intuition suggests. The frontier does not end there. In the digital landscapes of quantum computers, researchers simulate the paradoxes of time travel themselves. Using entangled qubits, scientists have recreated simplified versions of time loops, where information cycles through a circuit and returns to its starting point. In these simulations, qubits appear to interact with earlier versions of themselves, resolving paradoxes in ways that echo the Novikov self-consistency principle, the idea that events along a closed time loop must be consistent, forbidding contradictions. For example, when researchers programmed a quantum system to mimic the famous grandfather paradox, the outcome aligned with consistency. The simulation adjusted itself so that contradictions never occurred. The machine did not allow the destruction of its own past. Instead, it found stable outcomes where cause and effect coexisted, no matter how tangled. Such experiments are not literal journeys through time, but they offer glimpses into how the laws of physics might handle paradoxes if time loops were real. They reveal that even in the abstract circuits of computation, causality bends, reshapes, but does not shatter. Yet within these daring tests lies a profound caution. Physicists walk a careful line, balancing curiosity with restraint. Stephen Hawking once warned of a chronology protection principle, the possibility that nature itself conspires to forbid time travel in any practical form. His reasoning was that if closed time-like curves were allowed, the universe could collapse under runaway paradoxes. Energy fluctuations would build catastrophically, destroying the loop before it could exist. In this view, experiments that seek to tamper with causality may always meet silence, not because humanity has failed, but because reality itself is enforcing its boundaries. Still, the tests continue. In laboratories around the world, from photon chambers to superconducting circuits, scientists nudge at the edges of causality. Each negative result is not a failure, but a map of the frontier, narrowing the space where paradox might hide. And each strange anomaly, every unexpected interference pattern, every surprising simulation, is a reminder that time, for all its familiarity, is not yet fully understood. These experiments embody more than physics. They reflect the human spirit, the refusal to accept that time is an untouchable mystery. To test time is to challenge one of the deepest assumptions of existence. It is to hold a mirror to the universe and ask, does history bend? Can the future speak to the past? Or is time a fortress, impregnable, immutable? For now, the answers remain veiled. No particle has escaped into its own history. No photon has carried a message from tomorrow. But the experiments endure, as they must. Because the pursuit of knowledge is itself a kind of time travel, a reaching forward into futures not yet written, pulling them into the present with every discovery. And so, the laboratories continue their quiet work, one collision at a time, one photon at a time, one qubit at a time. Each test, each silence, each anomaly, brings humanity closer to the truth that time is not only a backdrop to existence, but one of its deepest mysteries, still waiting to be unraveled.
In the great puzzle of time, the past remains elusive, a realm tangled in paradox and contradiction. But the future is different. While legends and myths once painted time travel as fantasy, modern physics has revealed a truth more unsettling. Journeys into tomorrow are not only possible, they are already happening. This revelation was first written into the equations of Einstein's theory of relativity, where time ceases to be absolute. Instead, it stretches and contracts, sculpted by speed and gravity. Time, once thought to flow like a universal river, is revealed as a landscape, uneven and pliable. For some, the seconds slip by more slowly. For others, they rush ahead. The most direct evidence of this is not hidden in cosmic extremes, but in the orbit above Earth. On board the International Space Station, astronauts circle the planet at nearly 28,000 kilometers per hour. They live and work in microgravity, tethered to the thin shell of technology that separates them from the void. To the human eye, their lives seem ordinary, sleeping, eating, repairing instruments, gazing down upon the swirling clouds of Earth. But to the ticking of their cells, to the silent counting of their heartbeats, time itself has shifted. Due to their immense speed and the weaker gravity at orbital altitude, astronauts aboard the ISS experience time at a slightly slower rate than those on Earth. The difference is small, just milliseconds over months, yet it is real, measured with atomic clocks and confirmed with extraordinary precision. When they return, these astronauts are a fraction of a second younger than they would have been had they remained on the ground. In the language of physics, they have traveled into the future. This effect is not a trick of perception, not an illusion of perspective. It is written into the fabric of space-time itself. Time, for them, has literally moved at a different pace. The clock of Earth and the clock of orbit no longer align. If milliseconds seem insignificant, consider what unfolds when this principle is extended. Imagine a ship, not bound to the Earth, but racing outward into interstellar space, pushed to a velocity just shy of light. To those on board, years may pass, days filled with starlight through the portholes, with conversations and laughter, with the quiet hum of engines. But when they return, centuries may have passed on Earth. Civilizations would have risen and fallen. Languages, cultures, perhaps entire nations would have transformed beyond recognition. This is not speculation, but the direct prediction of relativity. The closer a traveler approaches the speed of light, the slower their clock runs relative to the universe around them. At 99.9% of light speed, a single year on board could correspond to decades outside. At even higher fractions, the gap grows dizzying, time dilates into vast gulfs, a corridor into the future. In this sense, humanity already holds the blueprint for time travel. It requires no exotic wormholes, no paradoxes, no violations of causality. It demands only velocity, or the crushing pull of gravity. Near the event horizon of a black hole, the warping of space-time grows so intense that minutes for a falling traveler could equate to millennia beyond. To approach such extremes is to step into a future unreachable by ordinary means. The unsettling truth is that time travel is not confined to science fiction. It is the ordinary consequence of physics. Every astronaut, every orbit, every particle accelerated in a collider is proof. Time travel is not waiting to be invented. It has already begun. But there is a catch. Unlike the imagined machines of fiction, this form of travel is one way. There is no return to the past, no chance to rewrite history or avert tragedy. The arrow points forward, relentlessly. For those who ride it, the journey is into tomorrows from which there is no retreat. This realization carries profound weight. To move into the future is, in some sense, to leave the present behind forever. A crew venturing to the stars at near light speed may find their mission complete in the span of a lifetime, only to discover that Earth has moved on without them, its people long gone, its world transformed beyond recognition. The voyage is both a triumph and a loss, a bridge to eternity, but also an exile from the present. Even here on Earth, the effect is inescapable, though subtle. Global positioning systems satellites orbit at altitudes and speeds where both special and general relativity shift their ticking. If uncorrected, the discrepancy would cause navigation systems to drift by kilometers each day. Technology has had to bend to the reality of time dilation, proving that relativity is not just a theory of distant stars, but a principle woven into daily life. And so humanity stands at a threshold. The question is no longer whether time travel is possible, but whether it will be embraced. The key lies in propulsion, in finding ways to reach the velocities where years can stretch into centuries. Projects like Breakthrough Starshot envision laser-driven sails, propelling probes to a fifth the speed of light, not enough to leap across millennia, but enough to begin. The dream of relativistic voyages is no longer fantasy, but engineering awaiting its revolution. Yet the philosophical implications may outweigh the technical. If the future is already accessible, what does this say about the nature of time itself? Does the act of traveling forward reveal that tomorrow already exists, waiting, fixed, and immutable? Or is the future still being written, moment by moment, even as relativity allows us to skip ahead? In this paradox lies the deepest mystery. Time dilation proves that clocks can disagree, that travelers may leap forward, but it does not tell us whether those futures are predetermined. It only shows that the flow of time is not equal, that the universe is more intricate than the ticking of a single universal clock. For now, the journeys remain small, milliseconds in orbit, fractions of a second in accelerators. But the principle is eternal, and its consequences vast. To travel into the future is to accept both wonder and solitude. It is to step into a tomorrow no one else has yet seen, and to leave behind a present that will never be revisited. Perhaps that is the greatest truth of all. Humanity has always been traveling into the future. Every heartbeat, every breath, every rising of the sun carries each life forward, one way, into tomorrow. Astronauts and near-light ships only make visible what was always true, that time travel is not a fantasy of escape, but the essence of existence itself. And so, while the past remains locked in paradox and mystery, the future stands open, a vast horizon stretching endlessly ahead. It is not a door waiting to be unlocked, but a path already beneath our feet, a journey every living being is already taking, 1 second at a time. At the limits of human knowledge, Science enters a realm that feels less like a laboratory and more like a cathedral. Equations become stained glass, glowing with symbols that hint at hidden truths. Each theory is a door, and behind it waits not certainty, but possibility. Here, in the frontier between physics and philosophy, time itself becomes unstable, stretched, fractured, or erased. One of the boldest visions emerges from eternal inflation, the idea that our universe may not be singular, but one bubble in a vast and ever-expanding sea. According to this theory, the Big Bang was not the beginning of everything, but merely the local birth of our own cosmic horizon. Beyond it, inflation continues, generating countless other universes, each with its own laws, constants, and histories. If eternal inflation is true, then time itself may not be one thread, but an infinite tapestry of branching timelines. Each universe would carry its own rhythm, its own unfolding of past, present, and future. To contemplate such a multiverse is to imagine that every possibility might already exist somewhere, worlds where time flows faster or slower, universes where causality takes unfamiliar shapes, or even realms where time itself loops and folds upon itself. From the immensity of the multiverse, some physicists turn their gaze to the smallest possible scales, the Planck length, where space and time may no longer be continuous. Here, loop quantum gravity suggests that the smooth fabric of space-time is woven from discrete units, like atoms of geometry. If this is true, then time may not be a river at all, but a sequence of indivisible moments, ticking forward in quantum steps too small to perceive. This discreteness raises unsettling questions. Could time be rewoven, its quanta rearranged like threads on a loom? If the universe is built from granular instants, could they be folded, reversed, or rewound? Such speculations reach far beyond experiment, but they press against the deepest mystery of all, whether time is a fundamental property of reality or merely an emergent illusion. Other theories turn not to structure, but to fragility. Within the equations of quantum field theory lurks the possibility that our universe exists in a false vacuum, a metastable state of energy that only appears stable from within. If so, then at any moment, without warning, a bubble of true vacuum could form, expanding at the speed of light and rewriting the laws of physics as it consumes the cosmos. Within its advancing wall, the constants of nature would shift, matter itself would dissolve, and time, as we know it, would simply end. This is not the apocalypse of myth, but a dissolution of reality itself. The future would be cut off, not by entropy or collapse, but by a silent transition to something wholly other, beyond comprehension. In this vision, time is not eternal. It is conditional, fragile, and finite. Alongside these vast frameworks, stranger and more speculative possibilities appear like glimmers on the horizon. The notion of tachyons, hypothetical particles that always move faster than light, suggests a universe where causality can bend, where effects precede causes, and where communication with the past might be possible. Though no evidence for tachyons has ever been found, their presence in the mathematics of relativity hints at cracks in the wall of impossibility. Equally provocative are the emerging ideas of time crystals, structures that repeat not in space, but in time. First proposed in 2012 and realized in laboratory experiments only recently, time crystals represent matter that never settles into equilibrium. Instead, they oscillate eternally, defying the conventional flow of entropy. Though they do not permit time travel, they challenge the assumption that time's arrow must always point in a single direction. Some theorists even sketch the outlines of temporal holography, inspired by the holographic principle that describes how information in 3 dimensions can be encoded on a 2-dimensional surface. If space itself can be holographic, could time also be projected from a deeper dimension, a hidden layer of reality where past and future are already inscribed? In such a framework, the flow of time might be nothing more than our perspective sliding across a timeless hole. These are not settled theories. They live at the edge of speculation, some tethered to mathematics, others still only whispers of imagination. But they share a common trait: they blur the boundary between physics and philosophy. For every equation, there is an echo of meaning. For every speculation, a reflection on what it means to exist within time at all. To explore them is not to claim knowledge, but to confront mystery. The multiverse invites the thought that our timeline is not unique. Loop quantum gravity suggests that time may be granular, finite, and malleable. False vacuum decay warns that time itself could end in silence. Tachyons and time crystals offer glimpses of realities that dance outside the ordinary flow. Temporal holography hints that past and future may coexist, hidden in a deeper order we cannot yet perceive. These ideas hover like constellations beyond the reach of observation, illuminating the night sky of human thought. They may prove to be mirages, or they may one day reshape our understanding of the universe. For now, they remain both scientific and philosophical, rigorous in their mathematics, yet poetic in their implications. And perhaps that is fitting. For time, more than any other concept, resists being captured. It is at once a measure and a mystery, a clock and a question. To peer into its depths is to discover not only the mechanics of the cosmos, but also the limits of human imagination. In the end, theories and speculations serve a deeper role. They remind us that knowledge is not a destination, but a horizon. Science may never provide a final answer to what time truly is, or whether it can be mastered. But in the striving, in the weaving of hypotheses and the testing of possibilities, humanity touches something greater than certainty, the wonder of existing, briefly, within the unfolding of time itself.
Across the ages, humanity has gazed not only at the stars, but at the passing hours, haunted by the same silent question: why must time move only forward? For beneath the mathematics, beneath the theories of relativity and quantum loops, lies a deeper force that no equation can fully describe: the longing of the human heart. It is this longing that first gave birth to the dream of time travel. Not through accelerators or wormholes, but through stories, myths, and memories. Time travel, at its core, is not only a scientific possibility. It is an ancient desire, rooted in regret, nostalgia, and the unyielding awareness of mortality. Every life is a sequence of fleeting moments, each one vanishing as the next takes its place. Within this transience lies the ache of impermanence. To wish for time travel is to wish that the arrow of time might bend, allowing what was lost to be reclaimed, or what is feared to be postponed. Psychologists have long studied the human relationship with time, and the findings are as striking as any physical law. Regret is one of the most powerful emotional forces in the human mind. It lingers longer than anger, burns deeper than sadness, and shapes memory itself. To imagine traveling backward is, for many, to imagine correcting mistakes, rewriting the fragile narrative of a life. Nostalgia, too, has its grip, a psychological balm that colors the past in softer tones than the present, a yearning for innocence, for the simplicity of what once was. But beneath these personal emotions lies the most profound of all, the fear of mortality. The passage of time is not simply the ticking of clocks, but the advance of finitude. Every second is a reminder that the future narrows toward an inevitable end. Time travel, then, becomes not just a dream of revisiting the past, but a rebellion against death itself. To step outside the stream of time would be to resist its final decree. Culture has carried these yearnings for millennia. In myths and legends, heroes venture into underworlds to retrieve lost loves, or gods grant mortals the power to glimpse tomorrow. In modern literature, science fiction has become the theater where these ancient desires play out with new precision. From H.G. Wells' The Time Machine to countless cinematic visions, the motif of second chances, of rewritten fates, endures. Each story is a mirror of our own longing, to undo, to preserve, to transcend. Cinema in particular has given time travel a unique power. On the screen, moments can be rewound, replayed, frozen in memory's amber. This reflects a truth of the medium itself: film is a manipulation of time, slicing it into frames, then reassembling it in endless variation. Perhaps it is no wonder that in the age of film, the human obsession with time travel has grown so vivid. Yet, there is more than yearning in this dream. There is philosophy. Time travel stories carry the existential weight of questioning whether life must be bound by impermanence. To imagine traversing time is to imagine liberation from its tyranny. It is a form of quiet defiance, an insistence that perhaps the river need not only flow one way. But science complicates this yearning. For while relativity allows journeys into the future, already happening in the slowed clocks of orbiting astronauts, the past remains elusive, barricaded by paradox. The idea of visiting yesterday collides with causality, with the very structure of logic itself. Physicists speak of closed time-like curves as a mathematical possibility, yet no experiment has revealed them. For now, the dream remains only that, a dream. And yet, this interplay between physics and psychology is revealing. The laws of nature may not permit the rewriting of history, but the human mind continues to attempt it, through memory, imagination, and narrative. Neuroscience shows that memory itself is not a fixed archive, but a reconstruction. Each recollection is a kind of time travel, reweaving the past from fragments. The brain edits, revises, and colors events, creating a past that is as much invention as record. In this sense, every human being is already a time traveler, moving not through spacetime, but through the shifting corridors of memory. This convergence of science and hope may be the most profound reflection of all. For the physics of time reveals its inescapable structure, forward motion, entropy, decay. But the human spirit resists, imagining universes where the past can be visited, where mistakes can be undone, where mortality itself might be delayed. The two perspectives, one grounded in mathematics, the other in longing, form a dialogue across the centuries. And perhaps it is in this dialogue that the true significance of time travel lies. Not in the engineering of wormholes or the search for exotic particles, but in what the dream reveals about humanity itself. To dream of time travel is to reveal the depth of our connection to time, our fear of it, our yearning to master it, and our inability to escape it. It may be that physics will one day deliver mechanisms we cannot now imagine. Near-light journeys to the stars, where centuries pass outside while only years pass within. Quantum experiments where causality flickers, hinting that the past may not be as immutable as it seems. Or perhaps the universe will deny us entirely, reminding us that time is the one frontier we cannot cross. But either way, the dream endures. It endures because it is woven into the human condition itself. To be conscious is to live not only in the present, but in the tension between memory and anticipation. To imagine time travel is to explore that tension, to ask what it would mean if the walls between yesterday, today, and tomorrow could be breached. And so, the dream of time travel is more than escapism. It is a mirror held up to existence. A reminder that life is defined not only by what is, but by what is lost, by what is hoped for, and by what can never return. In this way, time travel becomes not just a scientific speculation, but a human necessity, a story we tell to make sense of the brevity of life. As physics and psychology entwine, one truth emerges: time travel is less about leaving the present, and more about understanding it. It is a reflection of our struggle to live within the irreversible flow of time, and our yearning to transcend it. And perhaps that is why, even if no machine is ever built, the dream will never fade. For as long as there are regrets to amend, memories to cherish, and futures to fear, humanity will continue to imagine a way beyond the limits of time. In the silent laboratories of the present, humanity is already laying the foundations of tomorrow's questions. For though time itself resists capture, science continues to probe its boundaries, devising tools that may one day illuminate the edges of the temporal veil. The cosmos, vast and ancient, has left behind a message in light, the cosmic microwave background, the afterglow of the Big Bang. It is a map not only of space, but of time itself, carrying within its faint ripples the record of the universe's earliest instants. Future telescopes, sharper and more sensitive than any yet built, will turn toward this fossil radiation. They will search for subtle anomalies, distortions that might hint at exotic processes, perhaps even echoes of alternate temporal geometries. If time ever looped, fractured, or folded in those primordial moments, its traces may still linger in this faint cosmic static. Already, missions like the European Space Agency's Planck satellite and NASA's WMAP have charted the background with extraordinary detail, revealing fluctuations at the scale of millionths of a degree. But the next generation of instruments, the Simons Observatory, the CMB-S4 project, and spaceborne successors yet unnamed, promise to push deeper. Scientists hope these machines might detect signatures of gravitational waves imprinted in the first fractions of a second after the Big Bang, fingerprints of inflation itself. In these patterns may lie hidden clues, whether time is a singular river, or whether it once branched into many. Yet not all explorations of time unfold on cosmic scales. In the realm of the infinitesimal, researchers turn to quantum computers. Unlike classical machines, which march step by step, quantum computers weave superpositions and entanglements, exploring many pathways at once. Some theorists suggest they could simulate scenarios that flirt with paradox, models of closed time-like curves, loops in spacetime where cause and effect entwine. Though such loops remain theoretical, mathematics shows that quantum systems may behave differently within them, avoiding the logical contradictions that plague classical thought. A computer of sufficient power could allow humanity to test, in silico, whether time itself could fold without unraveling reality. Elsewhere, physicists experiment not with vast colliders or planetary telescopes, but with carefully tuned laboratories. Using superconducting circuits, lasers, and entangled photons, they attempt to mimic conditions where wormholes, hypothetical tunnels through spacetime, might emerge. In 2022, researchers reported a quantum experiment that simulated certain aspects of a traversable wormhole within a quantum processor. Though no actual tunnel was created, the model suggested that the mathematics of spacetime might be recreated within controlled systems, offering a glimpse of what artificial wormholes could reveal. If these efforts grow, laboratory physics may one day test not just the shape of matter, but the architecture of time itself. Each of these tools, telescopes, quantum processors, laboratory analogs, speaks to a common ambition, to transform time from an abstract mystery into a measurable phenomenon. Yet even as technology advances, the boundaries remain philosophical. What does it mean to simulate a wormhole, if no traveler can pass through it? What does it mean to detect a pattern in the cosmic background, if its interpretation remains uncertain? Science presses forward, but always at the edge where data and meaning converge. And it is here, at this frontier, that physics and philosophy entwine most closely. For as humanity peers into the deep past of the cosmos, or simulates the impossible with quantum codes, the ultimate questions remain not only technical, but existential. If closed time-like curves could exist, does that mean free will is an illusion, every event already written? If time can fracture, does identity fracture with it? If wormholes can be crafted in laboratories, does that not redefine the very scale of human potential? High-energy physics thus becomes not only an exploration of particles and fields, but a meditation on being itself. Experiments probe equations, but their implications probe meaning. Time, it seems, is not merely a coordinate in spacetime, it is the silent stage upon which existence itself unfolds. The coming decades promise discoveries that may reshape this stage. Detectors will listen for primordial gravitational waves, instruments will map the sky with precision beyond imagining, and quantum computers will unravel puzzles that no human mind alone could resolve. Whether these tools reveal cracks in time's armor, or simply reaffirm its unyielding flow, they will deepen humanity's understanding of the one dimension that none can escape. For in the end, ongoing science is not only about instruments and models. It is about humanity's relentless refusal to accept ignorance. Every telescope is a declaration that the cosmos will yield its secrets. Every computer, a wager that paradox can be understood. Every laboratory experiment, a promise that imagination will be tested against reality. Time remains the most impenetrable of mysteries. Yet with each generation, humanity arms itself with sharper tools, clearer vision, and deeper courage. The river of time may never be reversed, but with every discovery, the fog along its banks grows thinner. And perhaps, one day, a machine humming in a laboratory, or a telescope gazing into ancient light, will whisper the first true evidence that time is not what it seems. Until then, science continues, patient, methodical, unyielding, pressing its hands against the fabric of time, listening for the faintest tremor in its weave.
Time travel has always shimmered on the horizon of human thought, a mirage born of longing and curiosity. For every scientific equation that dares to bend the arrow of time, there lingers a deeper question. Why does humanity dream of escaping its grasp? Perhaps the search itself reveals as much about the human spirit as it does about the cosmos. Across centuries, from myth to mathematics, time travel has embodied desire, the desire to undo regret, to recover what was lost, to cheat mortality itself. Yet the physics that governs reality answers with paradox. Equations allow glimpses of loops, curves, and wormholes, but their stability remains fragile, their meaning uncertain. Again and again, the universe seems to whisper the same message. Time may bend, but it does not break. And this paradox carries its own profound poetry. Perhaps the impossibility of traveling backward is not a failure, but a safeguard. For if the past could be rewritten, history itself might unravel, cause and effect dissolving into chaos. By denying passage through its locked doors, time may be preserving coherence, the stability that allows existence itself to unfold. The refusal of time to yield may be the very reason there is something, rather than nothing. Still, even within its refusal, time offers strange gifts. It slows for the astronaut in orbit, it stretches in the presence of gravity, it reveals itself to be elastic, not absolute. General relativity shows that clocks can disagree, that moments are not universal. Quantum theory hints at deeper mysteries still, where time may not be fundamental at all, but emergent, a shadow cast by the entanglement of matter and energy. The very structure of the universe suggests that time is not what it appears to be. For humanity, this realization is both humbling and liberating. If time is not absolute, then existence is not merely a march toward oblivion. The equations reveal a universe more mysterious, more fluid than everyday experience allows. Whether or not travel to the past is possible, the very act of questioning time's nature has illuminated truths that transcend the dream itself. And so, the pursuit of time travel becomes a mirror. It reflects the deepest questions of the human soul. Why must life move forward? Why is loss irreversible? Why does mortality weigh so heavily? To ask about time is to ask about meaning, about purpose, about the fragile beauty of a moment that cannot return. The final irony is that humanity already communicates across time, though not in the way dreamers once imagined. Every night, the stars shine down upon Earth, their light a messenger from ages long past. The photons that strike a human eye tonight may have left their star before civilizations rose, before oceans shifted, before Earth itself knew its present form. To look upward is to see the past directly, woven into the night sky. In this way, the universe speaks across time, not through machines or paradoxes, but through the simple constancy of light. Perhaps this is the closest humanity will ever come to traveling backward, not in stepping into vanished days, but in receiving their echoes, carried faithfully across the void. The cosmos remembers, even if humanity cannot return. In this light, the dream of time travel becomes less about escape and more about wonder. For though the river of time carries all beings forward, never back, its current is filled with meaning. Every moment is both fleeting and eternal, fleeting in experience, eternal in its imprint on the unfolding fabric of reality. Nothing is truly erased, only transformed, woven into the vast continuum of the universe. The stars remind humanity of this truth. They are monuments of memory, glowing ruins of ancient times, reaching across light years to whisper that the past is never entirely gone. To gaze at them is to witness history written in light, an archive kept not in books or machines, but in the very structure of the cosmos. And so, the dream endures. Not because humanity may one day step into yesterday, but because the yearning itself defines what it means to be human. To dream of time travel is to declare that the fleeting is not enough, that memory longs to be more than shadow. It is to wrestle with mortality, with impermanence, with the profound mystery of being. In the end, whether time travel is possible or forbidden may matter less than what the question itself reveals. Time is not what it seems. It is both rigid and fluid, both a prison and a canvas, both unyielding and filled with hidden doorways. It resists mastery, yet invites wonder. The paradox remains: humanity flows forward, unable to return, yet always dreaming of return. And in that dream, perhaps, lies the true meaning of time. As the night deepens and the stars continue their silent watch, a final image lingers, light from the past, still traveling, still reaching, still illuminating the present. In that glow, the cosmos offers its answer. Time cannot be conquered, but it can be witnessed, contemplated, revered. And so humanity moves forward, not with machines to undo the past, but with eyes lifted toward the sky, listening to the ancient light and dreaming, always dreaming, of what might lie beyond the veil of time.